Vectors in C++ might be the most used data structure. However, most people use them wrong because they lack the fundamental knowledge of how they really work under the hood. If you have a background in maths, physics, or engineering, you're probably missing some implementation details, making your use of them extremely inefficient. In this video, we're going to take a look at an implementation that resembles the standard libraries implementation and will help you skyrocket your coding efficiency. Without further ado, let's dive right in. A vector in the math world is an object with a magnitude in a direction. In C++ though, it's just a collection of elements of the same type. For this whole video, we're going to use doubles as an example. So far so good. You already knew this, but as always, devils on the details. You see, while working in C++ and programming in general, there are two main sectors of memory you can use. They are the stack and the heap. The stack is really small and local to the thread of execution. You can think of it as your pockets. You can put your phone or your keys inside and out quite fast. Depending on the compiler you use, it can range from around 1 megabyte to 8 megabytes. The heap, on the other hand, is accessible by all threads, and you can think of it as a storage unit. So the access is way slower. You have to physically go there, unlock the door, and take your stuff out. I won't go into much detail, but just remember that the stack is quite fast and the heap is quite slow. So just try to use the heap as little as possible. Makes sense so far, right? Going back to a C++ vector, what it really is a dynamic array. Every time you hear dynamic, think about the heap. An array size is known at compile time, so you can just stack allocate it. A vector size can change over time, unlike an array, so there's just no other way but to allocate it on the heap and increase and decrease its size as needed. To achieve this, we'll be implementing two key functions, reserve and pushback. Reserve just asks your machine for memory, and pushback adds an element to the end of the vector. So if we try to push an element to the vector and we have no more space, we'll need to allocate some memory. The catch here is that in a C++ vector, every element must be adjacent in memory. So whenever you try to push an element and there is no more space, the machine needs to copy the whole vector into another memory location where there's more space. And that is really expensive. With some theory explained, let's take a look at what our vector can do. For that, I programmed this simple main function. I highly encourage you to stop the video right now and try to implement your own version of this. I assure you that this is a great exercise, and if you've never faced this before, it's going to take a couple of days probably. With that being said, if you need a little hint, this is the API for our vector, so the operations it can perform basically. Let's talk about them. You want to be able to construct your vector, so I've made a couple of constructors, and destroy it. You also want to be able to copy it and move it. If you don't know what I'm talking about, go learn about these basic C++ operations because you'll be needing them. Now for the actual implementation, we only need three things. The size of the vector, so the number of elements it currently holds. The capacity of the vector, so the maximum number of elements it can hold because of the memory allocated. And the elements themselves. The first two are pretty straightforward, but for the last one, since the vector lives in the heap, you need a pointer to it. This can either be a raw pointer, the asterisk, or a smart pointer, which is far safer in memory and should be preferred in modern C++, since it self-destructs when it gets deleted, so you can just forget about it and get a memory leak. Let's take a look at the CPP file. I made this constructor that just takes the size, and you reserve as much capacity as size, and you zero initialize everything with a std make unique. I also implemented an initialize_list constructor. Is this necessary? Well, not really, but it's always nice that you can pass in numbers in between brackets and get a vector from that. Now, what about the copy constructor? You need to pass a const reference so that you copy all of the members, so you initialize your own size and capacity to match that of the other vector, and then you reserve as much memory as the other vector had, and you copy every element from the other vector into your own vector if they have any. The move constructor is pretty straightforward. You just take the size and the capacity of the other vector and you move their internal array to your own vector. What that means is you just take the pointer to it, make it your own, and invalidate the other vector. The copy assignment operator allows you to do this if we are a vector trying to copy another one and this other one is ourself. So if we say v1 equals v1, we shouldn't really do anything, right? We'll just return this. Now if that's not the case, we need to copy the size and the capacity, as we did before, and all of the members with std copy, and we just return this. What about the move assignment operator? Well, this allows us to write this piece of code. So we do the same thing as before. If this vector is the one that we need to move, we just don't do anything. But if it isn't, we copy the size and the capacity, since doubles don't need to get moved, and we move the reference to the array, invalidating the other vector and returning this. Now, reserve is where the magic happens. So reserve takes a capacity, and if we already have that capacity in the vector, we don't do anything. But if we don't have as much capacity as they're asking for, we need to reserve that much space in the memory. So std make unique, and if we had any element in the vector before, we need to copy that to the new memory location. Once that's done, we move the pointer from our previous array to this new array, and we update the capacity. Having this reserve function, pushback function, is pretty straightforward. If the size equals the capacity, so if the vector is full, we need to reserve some more, and then we just use this index to add the element and add 1 to the size. We'll also need some way to insert an element into a concrete position in our vector, so we need to override the index operator, and that's pretty straightforward. We just need to check the bounds and return the array at that index, and to be able to look but not modify it, so returning a constant double, we'll do the exact same thing basically. And finally, in pretty much just for show, I wanted to override the output stream operator so that we can just print the vector instead of loop through it to print it. But for these, you need to declare this as friend. Why? Because from outside of the vector, you need to be able to look at its private members, and then you just redirect inside the stream your vector position by position, and that's it basically. Now with that, let's take a look at main. We can construct a vector and reserve memory for it. Then we add the elements and print out the result. Notice how we can just print out double vector instead of going position by position because we've overwritten the operator. There's also the initializer list constructor, the copy constructor, and everything we've implemented. So check that all of this compiles and works, and you have yourself a vector. Of course, we're missing some stuff like a pop function or some way to delete elements from the vector, but feel free to extend the class and make it your own. Oh, and by the way, remember that I said at the beginning that people use these vectors wrong? Well, how many times have you seen a vector being declared and then 10,000 elements get pushed back in a loop? Every single time that your vector runs out of memory, you have to copy the whole thing again. How many calls to reserve do you have to make? How many copies do you have to make? Well, how about you reserve the memory before you push back an element? This way you only need to reserve space once. Therefore, you can push back every single element that you need to push back and not make a single copy, saving a lot of time that can really build up. But maybe before this video, you wouldn't have understood the reserve function, so it just didn't make sense to you. Well, now it does. I hope this was useful and you learned something that you didn't know before. If so, let me know in the comments below. But for now, I'll see you in the next video.